Continue on now and do diffusion. If you remember, the expression in the Nernst-Planck equation has fixed first law in it, right? And that was the first term in the Nernst-Planck equation. So we have some species, say species O. So the flux due to diffusion is just the negative diffusion coefficient times the concentration gradient. So that's fixed first law. So where does this come from? It's actually pretty straightforward to derive this. I mean, we saw where it came from by the derivative of the electrochemical potential. Let's consider some location x along the x direction. Let's consider like a one-dimensional diffusion, and this is, think of it like a tube or something that exhibits one-dimensional diffusion. And then I have this partition at position x, and here I have NO species. This is going to be the number of molecules to the left, and then here I'm going to have NO of x plus delta x, and this is the number of molecules to the right, and they're different, right? Because there's some gradient in concentration, and this is a very small delta, right? Small delta. And so, of course, I have some fluxes, that are moving time due to diffusion. And so let's assume, very simply, a time step delta t. So if we have some time step delta t, that if we have random diffusion, right, and every molecule can say move delta x in time delta t, how many of the molecules here are going to move over here? These are delta x apart. So if I have random diffusion, how many molecules are going to go this way? How many choices and directions do they have to go? Two. So if they're equally probable, how many will go this way? Half of those, right? And how many of these will go this way? Half. Okay, good. So we can write that of x over 2, and the ones going that way are going to be NO x plus delta x. So during time step delta t, half in each side move either direction by delta x. So what this is basically doing is we're considering one-dimensional concentration gradient. We're dividing it up into infinitesimally small elements of width delta x, and we're saying the number of molecules in that element is given by these numbers, and every time step they'll go one way or the other way, right? And if there's a concentration gradient, this term will be bigger than this term. If this is bigger than this, the ones going this way will be bigger than the ones going that way, right? That kind of makes sense. That's basically diffusion from high to low concentration. But at a microscopic scale, it works like this. Think about it like that. So the net flux through area A, if I imagine this has some cross-sectional area A, right? The net flux at position x is just going to be given by 1 over A, because that's the area, right? Species per unit area, times the species moving from left to right, and O x t over 2, minus the species going from right to left. And O x, which is not t, x t, x plus delta x over 2 over delta t, the time increment. So that has the right units for a flux, right? Number of species divided by time divided by area. And some species are going that way and some species are going that way, so they're canceling each other out. Of course, at equilibrium, what's the next net flux equal to? 0, right? Because the concentration will be the same in both sides. So if I multiply both sides by negative delta x squared over delta x squared, then I get negative j equals squared over 2 delta t, and 0 x plus delta x over area delta x minus n 0 x times 1 over delta x. Okay, so I just took this expression and I multiplied by negative 1 on this side and -1 on this side. So I get the delta x squared. That's all that is, right? And this term here, what is this term? What's this at the bottom? Well, that's a length.
That's a volume.
That's a volume. And this is just a number, right? That's just a number. So that's a concentration. That's right, that's a concentration. So we define CO equals NO over A delta X. And I can now write this expression as -J equals delta X squared over 2 delta T CO X plus delta X minus COX over delta X. And I can identify this as the diffusion coefficient of species O in this case, or whatever species we're interested in. So it's sort of the how big of a step does it take in every sort of time unit, right? So it's basically, you can see this has the units of diffusion coefficient, length squared per time, centimeters squared per second is the units of diffusion coefficient. And it physically feels like a diffusion coefficient, right? Because if it takes bigger steps, it's going to diffuse faster. Or if it takes those steps more often, it's going to diffuse faster. And then if you take the limit, right, we let delta x goes to 0, delta t goes to 0. So I make time, but the limit is the time goes to 0 and the length of my partitioning, right? Remember, I'm slicing up space in these little delta x partitions. If I take that to 0, then it's just the limit of this, and what does this look like? dc dx, right? The change in concentration over the change in position. So we get our term here, which is -J equals d dc dx xt, and this is called Fick's law, Fick's first law. So if you think about it, this is due to a random walk. This is molecules randomly moving around with thermal energy. Step size, if you want to think about this, delta x is related to what's called the collision frequency. So how often they hit another molecule and have to stop moving. And delta t is related to the size of the molecule and how fast they move, right? You can generalize this to higher dimensions, d del c. So that's just the derivative in 3 dimensions, right? And we wrote it in Cartesian coordinates before. Okay, so that's Fick's first law. Introduced it phenomenologically at the beginning of the course. We said the diffusion rate is related to the concentration gradient. And now you can actually see a very simple model where that comes from. And it's kind of neat, right? That the derivative of the chemical potential gives you a Fick's law term. It better, right? Derivative of free energy tells you the driving force for stuff to move better be related to how much stuff moves. So let's look at this term, dc dx. I like to just, the best way to do is just with an example. X, positive x, negative x, right? X is increasing. What's the sign of dc dx? Positive, right? What's the direction of flux? Negative, right? So stuff's going that way. So the direction of the flux has to be opposite to the direction of increasing concentration. That's all I'm saying. Fick's second law, d CO x of t equals do d squared CO x of t dx squared. Okay, this is Fick's second law. We want to know where does this come from and how to think about this. One way we could just qualitatively think about this is imagine I have a concentration profile that looks like this. What's going to happen as a function of time? What's it going to look like eventually, Haku? It's going to be a flat line, right? With the average concentration everywhere. So this part has to go down, this part has to go up, right? So this is actually telling you that. What's the second derivative here? The slope is slope changing with position. Slope here, here, here. Slope is continually decreasing. So this term is what, positive or negative? This is negative. If I plotted dc dx, what does dc dx do? It starts high, it's decreasing, right? This is like 0, right? Here it's 0, here it's large, here's large and negative. And then, yeah, c dx squared, what's the slope of that? Negative, right? It's just a negative number, negative. Right, so this term has to be negative. What does that tell you then about the concentration? It has to be going down, right? And in fact, it's going down everywhere. Now, eventually that will change, right? Because I didn't put any boundary conditions in here, and basically, we're thinking about this as being an infinite sheet, and if it was infinite, yes, it would go down everywhere until it was flat. Now, if there's boundary conditions, we'd have to define those to solve the diffusion problem, and those boundary conditions gets more complicated. But you see the kind of the picture, right? So that's what fixed second law tells you. Fixed second law tells you how things change with time. And we define something steady state. What does steady state mean?
T equals 0.
Equals 0. Okay, so what does that tell you about the curvature? The second derivative has to be equal to?
0.
Okay, so this term equals 0 at steady state. So that's actually why, we mentioned this before, why we draw linear concentration gradients when we're solving steady state problems, because they have to be linear at steady state. Any curvature, they'll be changing with time. We can get second law from the first law by considering continuity. What does continuity mean? So in this context, imagine I had I carved up space into a bunch of blocks, right? And I had some J in and some J out. At steady state, what has to happen? J in equals J out. And if J in doesn't equal J out, what happens to the concentration here? It changes. It either goes up or down, according to this equation. Okay, so that's continuity. When people talk about the continuity equation, they're saying you can't create matter or get rid of matter unless you have like a reaction. So we can put in a reaction into our transport equation, say A goes to B, or electrons and holes recombine, or light comes in and makes electrons and holes, or we can put that stuff in, right? That's called recombination generation in semiconductor physics. Chemical reactions in electrochemistry. So we can put those things in, but if you don't have those things, you can't create or get rid of matter. So let's write this out. dc x of t dt. So the change in any unit is just going to be, as we wrote there, the flux in minus the flux out. And this is the change in concentration in element dx over time. And then we can write this term, I can write j x plus dx t equal to the flux at point x times the change in flux with position, the derivative of the flux with position times the change in position. So I can rewrite this equation, right, with a linear approximation, which is valid for dx, it's infinitesimally small, right? You can say, well, you have some flux at point x, and if I want to know the flux at a different point, I just need to know the change in flux times how far away I am from point x. And if dx is very small, this linear approximation works just fine. We'll label this 1 here. From 1, we can write dc0 or co x minus t dx t dt, sorry, not x minus t, x and t, equals these two terms put together, which gives you j x of t minus this term, which is going to have another jx of t in it, which I didn't have overlapping equations. Minus jx of t minus dj x of t dx times dx and divided by dx. Okay. And so that's actually pretty nice because this term cancels out, this term cancels out. And then I can write this term. Do you know anywhere I can get that term from? From fixed first law, right? Because first law tells me what J is, flux, in terms of concentration gradient. So I have equals d dx. That's that part. We're plugging in Fick's law, do dco xt over dx. And there it is. This is dc dt equals the derivative of Fick's first law. And often we take the do outside of this derivative. What does that assume? It's a constant, right? So it assumes that it has no dependence on the position or the concentration, right? Because the concentration is position dependent. And in fact, often you do have diffusion coefficients that depend on concentration for non-ideal systems or very concentrated systems. But often we take it out and we get the form that we wrote here. How do I generalize it to 3 dimensions? Del, right? Del squared C. And del squared, this is actually called the Laplacian. So we often do, in electrochemistry, we want to solve this equation, right? What do I mean by solve this equation? What I mean is we want to know the concentration gradient as a function of time. Because you think about, like, I apply a potential to my electrode, and I want to know the current, right? What do I need to know to calculate the current at an electrode? Okay, you need to know the concentration of the surface, right? Because, and why is the concentration of the surface important? Right, so we want that, right? Of O and R, right? Why is that important? So let's just say it's O plus an electron going to R. Why do we care about the concentration of O and R? How do we relate concentrations to current? It's the rate. Yeah. Is that what you said? Yeah. How do we calculate rates? Equilibria constants tell us equilibria. They don't tell us rates. You can count them. You can do it experimentally, but I want you to write an equation. Okay, how do we get the Butler-Volmer equation? I mean, the Butler-Volmer equation is one model to describe this, right? But what's a more general expression for the rate of, right? Okay, so the reaction velocity is going to be K, what's called rate, to make it simpler, K times CO, right? That's the forward rate, and rate backwards equals K back times CR. Okay, so that's why we need to know the concentration, for example, and you might want to know the concentration everywhere, right? But certainly if you wanted to predict the current, you might want to know this. So if you knew this at the electrode surface as a function of time, and you knew the rate constants, you could actually calculate the current response for the system, right? And so that's actually what we'll do in some of the following lectures. And how we do that is we solve this differential equation. And we're not going to spend much time at all in this class solving differential equations, because 1, I'm not very good at it. 2, computers can do it much faster than I can. And 3, almost all electrochemical problems that are interesting and apply to real life can't be solved analytically. So you solve them numerically. Okay, but you've got to know sort of what goes into it. So this is the diffusion equation, right? To solve it, we define boundary conditions. And you'll see how this is very important. And the boundary conditions define the problem. This equation always holds, right? But it's the different boundary conditions that give you the different solutions. So what's an example? I might say C0 x0 equals CO star. So what this is saying? This is saying for all x at time equals 0, you have the bulk concentration, right? That's a reasonable boundary condition, because before I pass any current, you just have to assume that the system is well mixed, right? That's reasonable. So that would be a boundary condition I might use. I might say the same thing, CR, x0 equals 0. No R, right? I can say that might be true. But if you made a solution of just ferricyanide and no ferrocyanide, right? You did that in lab. So that would be the initial boundary condition. And then I might define something called semi-infinite boundary conditions, and we'll define some of these later. For example, the limit as x goes to infinity in the positive direction of CO x of t equals CO star. So what does it say? So if you get very far away from the electrode, so if I say electrode at x equals 0, right? If I get very far away from the electrode, I get the bulk concentration. That's reasonable. What's very far? It depends. Depends on the time scale of your experiment. Certainly if your experiment is infinitely long, nothing will be far enough away. But on laboratory time scale, it's usually sort of millimeters, is far away from the electrode surface. And I might define the same thing for R, like I might say limit x goes to infinity, CR, x of t for all time equals CR, case of 0. So this is a semi-infinite boundary condition. This is an initial condition. And then the third type of boundary condition I might want to define is an electrode surface boundary condition. So I might say that CO of 0t equals some function of potential I apply, right? So if I'm controlling the potential and I want to measure the current, or I want to predict the current, I should say, what I need to do is predict the O and predict the R. And so I have to make some assumptions here. I could make some assumptions here to get that. So for example, if I have really fast kinetics, what would be, for example, a function that related CO of R to CR of R at 0t? So for all time at the surface, so if kinetics vary fast, what kind of function can I use to relate this to electron potential? The Nernst equation, exactly. Right? So we'll do that next time. We'll talk about how this works. We're not going to solve the differential equations because gets tedious. You have to use various Laplace transforms. It's just a pain, and this doesn't really add much to the course. But you can look at the book, and it goes through it if you are interested in the math, and it'll be a lot of fun.